Hi students, in this third part for online lecture 5, we are now going to talk about the various shapes of our orbitals. So we talked about on our last video the idea of the quantum numbers, which are a mathematical simplification of Schrodinger's wave equations. So now what we need to talk about is the existence of the electron in those wave functions. So what we are talking about is that this mathematical equation says where an electron should be. So we can come up with the idea of the Pauli exclusion principle. No two electrons can have the same four quantum numbers. This is stating that we are not allowed to have the same wave function equation. One of the terms must be different for each electron. So seeing that the wave function is used and simplified to create the quantum numbers, the Pauli exclusion principle saying you cannot have the same four quantum numbers means that your wave functions must be different for different electrons. So what does that mean? Well, let's talk about it as a seat number when going to a football game in Kyle Field. If you have a ticket and have a specific seat, no one can sit in that seat. It is your seat. The person next to you has the same section in the same row, but they do not have the same seat number. So they have one small difference. Now, there may be a lot of seat 14s or there may be a lot of row 12s, but there may be different sections. So this is how I want you to look at an electron and its possibilities in an atom is having some variation in our quantum numbers to give it a different location. Each seat can only hold one individual at a time. So for our quantum numbers, if an electron has those four quantum numbers, no other electron can have them. However, we can now make some assumptions and classifications. We can say that electrons are in the same shell if they have the same value of our principal quantum number. This is like saying that a large group of people are seated in the same section. That section might be 52, and it comprises of all of those people, but it doesn't give us a real defined idea of exactly where they should be. If we then take our shell and start to divvy it up, we can get to our subshell. These are electrons that have the same first two principal quantum numbers. This would be taking our section, 52, and now talking about specifically people in row 13. We have taken a large group of people and now given us a subset of those. We're becoming more specific. Finally, we can then go to an orbital. An orbital, by definition, are electrons that have the same first three quantum numbers. These terms are going to be used all the time when discussing not only our electrons, but sometimes referencing back to the periodic table. So you need to be able to describe them very easily. A shell is typically our largest group and means only one quantum number, our principal quantum number being the same. If we make the first two quantum numbers the same, we get a subshell. And finally, if we have three quantum numbers, the first three, then we have our orbital. So let us look at an s orbital. The nice part about this is that this is a three-dimensional volume. We are now going to start talking a little bit about what incorporates that volume. So for an s orbital, you will see that it's shaded here in green, but it's really a three-dimensional space. If I were to take a 90% confidence interval of where that electron density should be, so that means that there's still a possibility of 10% maybe being outside of it, I can now get a circle. This was a true assumption by Bohr when dealing with his Bohr model. He was seeing the two-dimensional representation because he was using hydrogen, which only had one electron, which is in a 1s orbital. But now as we've gone further and further, we now know that this is a three-dimensional volume. So as Bohr was doing his work, he was only seeing this radial distance that we see here as his principal quantum number and his distance. But that's not true to its entirety. What actually happens is that it's now that distance in 3 dimensions. This is how we get the s orbital to be a sphere. So the spheres that we are drawing are actually just a mathematical cage per se that an electron has a 90% confidence interval being inside of that volume. Historically, the electrons want to be as far out in that volume as possible because it doesn't want to go towards the nucleus because of the opposite charges. But for the most part, our s orbitals have a very defined, distinct location and distance. So now what we can do is go and picture the p orbitals. Notice that the p orbital, our L being equal to 1, has a different volume, and we are given 3 orientation possibilities. Well, what does that mean for us? Well, as you'll notice, we have the 2px orbital, the 2py, and the 2pz. We label them based off of the coordinate axis that is there. Another issue is that we have what is commonly called a nodal plane. When dealing with our L values, which is our second quantum number, this will tell you the mathematical possibilities of where an electron can't be. So let's look at the 2pz orbital on the right. Notice that there is a plane located right here in which the electron can't be. This means that the electron density, the possibility of an electron being there, is 0. We actually are going to call that a node or nodal plane. So as you're going to increase your L and your differences in your subshells, you are going to end up with more mathematical possibilities with more nodes. So then when we look at our orbitals, notice that we have our 3 different orbital types here. I can assign this as possibly -1, 0, or +1, or you could assign them any other way. So now let's go look at the d orbitals. Notice that they are much more complex. For our L equals 2, we would need to have 2 nodal planes. Notice you can see the first nodal plane very easily right here along this axis. Then there would also be another one that would be perpendicular to it going in between those as well. You can see them here on the 3dxz. One would be right through here. And then finally, you would have one going vertically along the coordinate axis. So notice that I get 2 nodal planes. The interesting part about all of this is what we do when we add the volumes. So the s orbital, because there's only one, has a uniform distance and a sphere located around the coordinate plane. If I were to go and add all of my p orbital electron densities together, you would come to find out that they would observe and create a sphere that's slightly larger in size than that of the 2s orbital in the location. So what was happening is Bohr was actually seeing the constructive interference of our wave functions and all of our mathematical possibilities added together. He was not able to discriminate and discern the individual orbitals. He was able to see shells and subshells, but now the math allows us to picturize our orbitals. We can also do the same for our d orbitals. If we were to add up these 5 possibilities together, we would end up with a larger sphere as well, all incorporating our coordinate plane. So as you're looking at these shapes, it's important for you to notice that each one of them has their own differences. The s orbital being spherical, the p orbital has electron density historically centered over a coordinate axis, but having at least one nodal plane in which electrons can't be. And then finally, we get to our d orbitals that become more complex. You will also notice that I haven't showed you the f orbitals, but they would have 3 nodal planes, and they would be much more difficult to picture, and you can find them in your textbook very easily in this chapter. So in this video, you are able to now picture our orbitals, which are actually the creation of a mathematical equation now picturized to let us know where electrons should be. In the next video, you're going to see why these shapes, as well as some of the fundamental rules, will now limit the possibilities of where our electrons should be. Have a great day.